Okay, that's the recording and the transcription started. So usual caveat, if you are not keen on being recorded, don't say anything while we're in the recording part, and I'll ask again if there's questions when we're done. Okay, so today I want to talk about processes again. See, that was going to be so cool. I was going to say, I want to talk about processes again, and the process diagram is going to appear, except I've managed to put it on. Oh, actually, it wasn't me, it was on this screen, but Windows decided to put it on a different screen. So we're going to talk about processes again. We're going to talk about process scheduling, because we talked about processes and this process schedule diagram a couple of weeks ago, and we talked about how processes can come in, be ready to run when they get the CPU, start running, and either exit if they are finished running. They can go to a waiting queue if they're waiting in some I/O, or if they just run out of CPU time, they can go back to a ready state. So what I want to talk about today is how that works, some strategies for how that works, and some of the theory underpinning different approaches to how we might set it up. Okay, so there'll be a few of them, and as so often with this, what I'll be saying quite a lot is, well, it depends. On the one hand, but on the other hand, oh no, it's about a matter of balance. In other words, there's no right answer for these things. There's only the answer that works best for your operating system, with your hardware, with your mix of work. All of those things can affect the scheduling that you have and decide to use. So we will look at a few different types, and I'll try and give you the pluses and minuses for all of those, so that you can understand why particular systems have been chosen for particular operating systems. But remember what we said a few weeks ago. We talked about processes and their characteristics, specifically whether the process was CPU bound or I/O bound. And we defined it as saying, well, okay, you're watching PowerPoint. PowerPoint, at the moment, is I/O bound. In other words, PowerPoint's just waiting on me. It's waiting on me clicking a button. It's not doing anything. It's not needing to update. It's not needing to run anything. It's done what it needed to do. And now it's just waiting on me and updating. On the other hand, you're watching this on Teams, and Teams is CPU bound. There's a lot of CPU involved in making the chat appear, making the video appear, making it change. CPU's involved in that. But on the other hand, Teams, you're probably not doing any I/O whatsoever. Of course, it's a lie. Of course, Teams is doing I/O, because remember the second part of I/O is output. So don't just think of it in terms of us doing things with the program. Think about it in terms of the program doing things with us. So for Teams, it's updating these videos. That's output. It might be updating the chat column. That's output. Okay, so it's input and output. If you're running an end of month accounts package that's going to print off all your invoices, well, it's going to calculate the invoice a lot faster than your printer will print it. It's I/O bound, but in this case, the I/O is the O side, the output side. So regardless of whether it's I or O, most processes can be characterized as either CPU bound or I/O bound. And even where they can't, there will be times where they do some CPU and times where they do some I/O. So you'll get a burst of CPU, a burst of I/O. And of course, while you're waiting in that burst of I/O, you can't do anything with the CPU. So one of the things we want to make sure is that if we are waiting on some I/O, we don't have it in the running queue. We don't even wait until it's finished the time it gets. We just say, nah, you need some I/O, go away, wait till that's done, and then come back and we'll talk. We can actually go further. We can characterize it. So we can look at existing systems and we can try to figure out what a CPU burst looks like. Now, again, different operating systems, different hardware, different mix of workload will show different graphs. But here's an example one. And you can see that the CPU burst times in the main are very, very short. Remember what a millisecond is? Everybody know what a millisecond is?
Millionth of a second.
You'd think so, but no. Good
It's
try
either
though.
100th or 1,000th.
Well, we talk about hedging your bets. It's 1,000th. So a millisecond is 1,000th of a second. So we can see here that the most used time for this particular system is just over, well, we'll say it's 150 millionths of a second. Oh, Alan, you get me going now. 150 thousandths of a second. In other words, very, very short time. Let's put that in context. How fast do you type? Might be, say, 40 words a minute if you're doing well. Say an average of 5 characters per word is 200 characters a second. Sorry, 200 characters a minute, which works out at 1 character every third of a second and a bit. A third of a second is, well, my screen's not big enough. It's double the time that this CPU burst is. So think of the amount of work that can get done just between you pressing a key and pressing the next key when you're typing. That's the sort of thing that we are making use of. The fact that there are gaps, and the gaps might not be much to us, but to that CPU and to your processes, those gaps are excellent. Okay, so we've got all these processes. We want to run them, and we want to run them in the most efficient way possible. And we talked about how we might do that. And I want to go into detail, but before we go into that detail, I want to think about the difference between preemptive and non-preemptive. Spoiler alert, big blue characters on the PowerPoint, probably something you want to remember. So we've got ways of moving within our state diagram. Here's our state diagram, and there are lots of ways we can move between these different states. All these lines are ways of moving. And what it's suggesting in the slide there is that we can go from running to waiting, so we're waiting in I/O. It can switch from running to ready, so it still needs more CPU time and it hasn't finished. It can switch from waiting to ready, so the I/O has completed and now it needs some CPU time, or it can finish. If we think about running to waiting or running to ready, if we think about running to waiting or running to exit, both of those are non-preemptive. In other words, the process has finished. The process has done what it wants to do. In the case of exit, that's clear, it's finished, it's exiting, it's done. In the case of an I/O event, it's done what it needs to do in terms of the CPU. So this is what this really means, CPU time. On the other hand, the other ones, where we switch from running to ready, or go from waiting to ready, are preempted. So what we're saying is the operating system has decided that the process is running, it's had enough time because there's other processes waiting, so it's going to preempt that process. It's going to say, no, go away, go back to the ready queue, and what I'm going to do is dispatch another process and give it some time. So this idea about switching processes at the behest of the operating system is preemptive. So the operating system looks at the process, says, nah, you've had long enough, go back to the ready queue and I will choose something else. Actually, the same thing happens with waiting to ready. It's preempted. In other words, the process has had its I/O, so you preemptively move it to ready to show that it's ready to go. The process doesn't have any say in it. So all of the stuff that we're talking about in terms of the scheduler and how processes move about within that sequence can be thought about in terms of preemptive and non-preemptive. And the thing that does that, as you probably saw in the diagram, is the dispatcher. It takes control of the CPU and it gives control to whichever process is next. So the scheduler decides which one's going to be next. The dispatcher is involved in the process of actually doing it. And remember, we spoke about that a couple of weeks ago in terms of what was required. Remember, a process is running. It has a whole set of states. Which instructions are at? What are the registers looking like? What's the instruction register? What's the accumulator? What about all that state data? We'll need to save all that. We then need to load in the new process state data and start moving to restart that process instead. That clearly takes time. So one of the key things that we want to think about when we're deciding which of these approaches we are going to use as the best, where best is very much in inverted commas, is something we call the dispatch latency. In other words, how long does it take to switch this process? How long does it take to save that state, move it out, move in the other one and get started? Clearly, we want that to be as short as possible. And in fact, we've got a whole bunch of criteria. So that's for dispatch. For scheduling, we've got a whole pile of other criteria that we want to use. Other operating systems may vary. Other operating systems may put more or less emphasis on any of the ones that are identified here. But what we want to do is say we've got a CPU, let's try and keep that as busy as we can. We don't want the CPU sitting there doing nothing. We also want all these processes getting through as quickly as possible. We don't want processes sitting there forever. We want to get them through as quickly as we can. We want from the start of the time where we start the process to the time that process ends, it's called the turnaround time. We want that clearly should be as short as possible. Now remember, when we're talking about these things, this is where it's really important to, in your mind, differentiate between a program and a process. I may be running PowerPoint, but I'll be running the move the mouse pointer process. So that process where I moved the mouse pointer and it redrew, started and ended. Done. So that process was in there, it executed, it finished. But the program, PowerPoint, is still going. So make sure you have that clarity in your head between a program and a process. And you remember when I looked at my machine, I had literally hundreds of processes running on my machine, even though I only had, I think, 3 or 4 programs. So we want turnaround time to be as short as possible. Why? Because if I move my mouse, you want that to happen as quickly as possible. You don't want me moving the mouse to be sitting there. You don't want it. You don't want the system to be doing something else. So when I move the mouse, and I'll pretend I've just moved the mouse, nothing happens, and then eventually it catches up and moves the mouse. And actually, you've all felt that. I would be willing to bet you've all felt that in a computer where you go to move the mouse and it doesn't because it's doing something else. So you go to type a key and nothing happens. So you type the key again, then you do it again, and you end up with 20 X's because it didn't appear on the screen immediately. That's because these things haven't worked as well as we hoped they would. We didn't get the throughput going. We didn't get them to turn around quickly. And particularly, the waiting time went wrong. We had to wait too long for the process to actually start. Again, because the system was doing something else. So the waiting time is how long it's been in the ready queue. In other words, it could go if it had the CPU, but it hasn't had the CPU. And finally, the response time. And that's different to the turnaround time. Turnaround is completion. Response is first response, not necessarily completed, which is why you quite often see on programs like timers. So you go to print something, and the first thing it does, it puts up a wee box and says printing 0%. Because you can do that response time really quickly so that the user knows that something's happening, even if the process time will take longer. So these are the criteria that we're going to use when we look at these different approaches. And of course, clearly, we want to have the most CPU time used that we can. We want to have as many processes through as we can. We want them to wait for as short a time as possible. We want them to be finished in as quick a time as possible, and we want the response to be as quick as possible. Okay, so as we're looking at these, think of these criteria and whether or not they fit in with these approaches. Everyone happy with that before we start looking at specific approaches to scheduling? Anybody get any questions or any comments before we move on to? Okay, let's look at our first one then. The first one is a really simple one. First come, first served. So you're going to see a lot of these diagrams. So I'll take a wee minute just to explain what we're talking about. So you can see a column with processes. They're identified with P and then a subscript. So process 1, process 2, process 3. And then we have something called the burst time. How long does that process take to complete? Now, the one thing that we haven't put against the burst time is any sort of sense of the unit that we're using. So we don't have milliseconds or microseconds or seconds or anything against them, because in essence that doesn't matter. That's down to the hardware, and if the hardware can go faster, we'll do more. These are time quantums. They are periods of time. So whatever the period of time is, we can apply it to all the types of hardware that we have. So if you've got a faster processor, it still takes 24 periods of time, but the processor might be going twice as fast, so that takes half the amount of elapsed time. So we've got processes, they are arriving into our process queue. So new processes are admitted, they're in the ready queue. And we say we're going to take the first one that came in. So the next bit is this line here, and this is CPU. Okay, so the first process comes in, it gets the CPU, and it gets the CPU from 0 to 24, which matches up with that burst time. It's taking 24 units of time. We then have process 2, it's got 3. Well, if process 1 finishes at unit of time 24, and process 2 takes 3, then process 2 will finish at unit of time 27. And similarly, process 3 will start at 27 and finish at 30. So we've got all our processes, they've all arrived, they've all been run. It's taken the cumulative time, 30, to get them all through. Everyone happy with that before we start calculating things, because we're going to be using lots of these over the next half hour. If you have any questions on this, now would be the time to ask. Okay, so remembering our criteria, we can start to calculate how well we're doing against those criteria. So we said that we wanted, for example, waiting time. How long does it wait for each process to start? Well, process 1, and remember they all came in, they all entered at time 0. Okay, so they all came in at time 0. Process 1 came in at time 0, didn't have to wait at all, so its waiting time was 0. Process 2 also came in at time 0, but it had to wait until time 24. Process 3 had to wait until time 27. So we've got 3 processes, we add them up. 0 plus 24 plus 27 is 51 divided by 3, which gives us our average waiting time of 17. On average, processes waited 17 time units to get done. Of course, we've taken these in the order they came in. What if they came in a slightly different order? What if process 1, rather than coming in there, had actually come in there? So in effect, we had P2, P3, P1. Well, our chart's going to look very different all of a sudden. P2's come in first, finishes after 3, P3 then starts, finishes after 6, and then P1's done. Our waiting time looks very different. P1, we took until 6. P2 didn't wait at all, and P3 only waited until 3. 6 plus 0 plus 3 is 9, divided by 3 is 3. In other words, our average waiting time went from 17 to 3, just with the difference in the arrival time. Thank you very much. He's up. Cheers. So you can see that first come, first served scheduling is very reliant on the processes and their arrival time. And if you want to think about it, any of you who drive or have been in a vehicle stuck behind a big truck on a single track road, will know exactly how this feels. If you were in a car on that road, you could go a lot faster. But because the truck got there first, it's got to get through, and you've just got to wait behind it to get through as well. So that's why we call it the convoy effect. Shorter processes get stuck behind longer processes. So it seems like first come, first served probably isn't our best approach. So let's think about how else we might do this. Well, when we're looking at first come, first served, the obvious, helps if I do my thing on the screen that you can see. The obvious thing that we see here is the short ones are at the end here as opposed to at the start here. So maybe we could come up with some approach that was about taking the shortest ones first. We'll call it shortest job first scheduling. Of course, the only question is, and if we go back to our car analogy, it might be that process 2 is some teenager in a Corsa who's running along that road at 90 miles an hour. But it could also be an 80-year-old granny in a Suzuki who's trundling along at 15 miles an hour. How do we know, in other words, what the shortest job is beforehand? If we actually knew how long processes would take, if we knew how long each process would take to complete, we could actually always be sure that we were running the optimal strategy. It would give the minimum average waiting time for a set of processes every single time, but only if we have complete knowledge, if we know how long the processes will take. Let me give you an example. So there's 4 processes with different times, and we simply look at them and say, okay, what's the shortest time? Well, P4 will take 3. So we'll take that one first. It starts at 0 and runs to 3. We've done P4, so what's next? 6, 8, 7. Well, smallest one for that is 6. That's P1, so we'll do P1 next. It starts at 3 and goes on to 9. 2 left, 8 and 7. Shortest of those is P3 that takes 7, so we'll do P3 next. P3 pops in here, starts at 9, goes on to 16. And finally we do P2, which starts at 16 and ends at 24. So our average waiting times are 0, 3, 9, 16. Added together, divided by 4, gives us 7. We cannot do better in terms of waiting time. However, this assumes that we know this stuff here. It assumes that we know the bus time. And it can be very difficult to know how long a process will take. We can estimate it. If you're running a process and you give it some CPU time, chances are it will probably take much the same time it took the last time. So we could maybe take a note of that and say, oh, well, this is quite a heavy CPU one. Last time we do it, it took 24. So chances are it will take 24 next time. So we'll put a notional 24 against it. We can actually finesse that. So rather than just looking at the previous one, we look at all of the previous bursts that it's been given to see how long it's taken. That might not work out quite as well because there might be different CPU times at different parts. So what we can do is give less weight to busts that were taken longer ago. So the most weight is we give to the last one, slightly less weight to the one before that, slightly less weight to the one before that, and so on and so on. Which is what this slightly scary equation is doing here. It's called exponential averaging. And if you don't know what that is, don't worry about it. If you're not good at equations, don't worry about it. If you don't know a theta from an alpha, don't worry about it. I imagine that Greek wasn't first on your list of things to learn when you came into computing. So don't worry about the process behind it. Trust people who know far more about maths than I do, that this is the right way to do it. It basically is a rule of thumb that smooths out a time series. So rather than saying, so we can chart how long each process took when it's been given some time. And you can see that there's quite a change there. What we're trying to do is guess how long it will take. So at the beginning, we guessed 10, it took 6, so we adjust our guess. Well, what about 8? Well, actually that time it took 4, so this time we'll guess 6, and we're spot on. So we've been going down on, so let's guess a wee bit less, let's guess about 5. Oh, this time it was 6, so we'd better guess a wee bit higher. All we are doing is trying to smooth out what we have, so that our guess approaches what we want to do. So it's important. You have to remember that we have something called exponential averaging, but you don't have to remember what the equation is. And you certainly have to remember that we have a preemptive version, in other words, one where the operating system takes charge and says, hello process, go away, you've had enough time. That's called the shortest remaining time first approach. Again, if you're interested, a wee bit of an expansion of the formula. Feel free to look at it. If you're into those kind of things, feel free to jump over that slide if you're not. But don't jump over this slide. So here we've got an example of shortest remaining time. So remember our idea here. We have got some processes that are arriving into our ready queue. And they're arriving at different times. So now we're not assuming they'll arrive at once, they're arriving at different times. They're arriving in the order that you see here. Arrival time 0, 1, 2, 3. So we're adding an extra column into our table. So we can look at our time across our x-axis here, 0 through to 26. And we can say at time 0, looking at this, actually the only process we have is process 1. There's nothing there because it's at time 0, these haven't arrived yet. So it's a dead simple choice. Give the CPU, give process 1 the CPU. At time 1, process 2 pops in. Now here we've got a choice. We've now got 2 processes. They're both in the queue now at time 1. And we have a burst time. Now we need to update our burst time. Why? Oh God, he's asked a question. Do I need to, oh, what did they say? Why do we need to update our burst time now? Because we've already given it some CPU time. Come
Yeah,
on.
sorry, I was trying to find my headset. Is it because obviously now we're at 1, so the burst time will go down to 7?
Exactly that. So we've had that 1, So our bus time is now 7. So at time 1, process 2 has arrived. Process 1 is already in there at bus time of 7. So we've got a 4 and a 7. We compare them and we say, sorry, process 1, you've been preempted, go away. We take it out of the running mode, put it back into ready, and promote process 2 into running. So process 2 comes in. So process 2 gets 1 time quantum, and then at time 2, process 3 arrives. So again, at time 2, why does it keep forgetting I'm using a pen? At time 2, process 2 has had a chance to run, and it's also changed, and it's gone down from 4 to 3. So at time 2, we compare process 1 with 7, process 2 with 3, and process 3 with 9, and say, oh no, right, you're cool, process 2, keep going. Same thing happens at time 3. But of course, process 2 has already had another shot, so it's gone from 3 to 2. So at time 3, we've got process 1 with 7, process 2 with 2, process 3 with 9, and process 4 with 5. So still we have the shortest time remaining being process 2. So we let it continue, finish off. We know that it came in at 1. We know that it took 4, so it ended at 5. Process 2 is done. So at time 5, we go, okay, what we've got left? We've got process 1 with 7, we've got process 3 with 9, we've got process 4 with 5. Okay, we want the shortest remaining time first. We jump to process 4. So at time 5, process 4 goes in, gets its 5 and taking its way up to 10. Process 4 is then done, and we do the same thing. We've got 1 at 7 and 3 at 9. So 1 comes back in, and it gets to finish off. And then finally we get process 3. The average waiting time now gets a bit trickier. So process 1 started at 10, but it finished at 1 before, so it's 10 minus 1. Process 2 started at 1 and came in at 1, so it's 1 minus 1. Process 3 started at 17 and came in at 2, so it's 17 minus 2. And process 4 started at 5 and came in at 3, so it's 5 minus 3. Work all that out, divide it by 4, and you get 26 over 4, or an average waiting time of 6.5. Everyone happy with how that was calculated? Any bits of that you want me to go over again? If you're happy, give me a thumbs up or something. Just give me some sort of response to know that you're not sleeping.
All right.
Thank you. Okay, so we've had some approaches. Maybe there's other things that we can do. Maybe you don't want to leave it up to the operating system all the time. Maybe you want to give the user some control over the things that the user wants to do. Maybe you're running an Android and there might be lots of processes running in there. But while you're on the phone, you kind of want the process phone to be taking all the CPU time it needs so you can keep talking to somebody. So maybe we can start to give priorities to processes. Just give them a number and say, yeah, this one is more or less important than another. We already do that. We already give priority to things like interrupts. So if an interrupt comes in, we service that first. So we're already familiar with that idea. Maybe we can extend that away from the kernel space, so controlled by the operating system, into the user space, controlled by the user. In a sense, what we're doing with shortest job first is also prioritizing, but the sole criterion we are using to prioritize is the predicted CPU time. Maybe we can do something else. Maybe we can give processes priority. Now, we need to be careful, partly because users are users, and if you're on a shared system, every user thinks their work is the most important and should have the highest priority. We also need to be careful about processes that actually are low priority, but there's so much work coming through, they stay low priority. So a low priority job comes in, higher priority jobs get done, and they finish, but in the meantime, there's more higher priority jobs get done, and this wee poor low priority process stays at the bottom and never actually finishes. That's called starvation. We never give the process any resources to get going and doesn't execute. So one of the approaches we use for that is something called aging. Even though it came in at a low priority, we keep an eye on when it came in. And if a certain time has gone past, we raise its priority. And we keep raising its priority until at some point it becomes a high enough priority to be above all these high priority things that keep coming in after it, so it will eventually get done. And that's called aging. So again, let me give you an example of priority scheduling. Again, we've got an extra column here, or a different column. We've still got our processes, we've still got how long we think they'll take, but we've now got a priority. So we're assuming these all come in at the same time. And we simply look at them and say, okay, what's the highest priority? Highest priority is process 2. We do that one first. Dead simple. Do process 2. It's got a burst time of 1. It goes from 0 to 1. Process 2 is done. I keep pointing onto the screen I'm looking at instead of the screen that you can see. Somebody should remind me when that big yellow blob's not there.
I do the same.
So process 2 has priority 1. So we run that first. So that goes in and runs. It's got a burst time of 1. So it starts at 0, goes to 1. Process 2 is finished. And we go back. So we've got a 2, 3, 4, 5. So the next one is process 5 with a priority of 2. So it starts up at time 1. Burst time of 5, so it goes to 6. And then P5 is finished. So we've got 1, 3, and 4 with priorities of 3, 4, and 5. So the next one up is P1 with a priority 3. It comes in at 6, runs to 16. And then P1 is done. And then we've got a final 2, P3 and P4 with priorities 4 and 5 and a total of 2 and 1 respectively. Everyone okay with that? No one's got any problems with that at all.
Tony, sorry, I'm not sure if I'm blind. I don't see P5 on that Gantt chart.
Thank you. So all this stuff is right. All the numbers down here are right, and all the calculations are right, but the P's on here are incorrect. So you can see here we said highest priority was P2 with a priority 1, but you see here it's P1. So these times are all right, and your job now is to grab that Gantt chart and change it. So for example, P2 should actually be, P1 should actually be P2. Okay, all the times are right and everything else is right, but I want you to go back and update it and get it right. And you can blame Silberschatz, Galvin, and Gagne for that one. It wasn't my fault, I promise. And if I was being snarky about it, I could ask why nobody had looked at this stuff in advance to see that big exclamation mark and warning to say that slide 19 is mislabeled. It's almost like you didn't read ahead. Shocking. Shocking. Okay, let's look at another approach that we might want to use. And this one is called round robin. So the idea here is that we have a whole bunch of processes. They all need time. We probably don't know what that time is without being able to see into the future. So maybe we can go at it in terms of fairness. Rather than trying to work out when they came in or which one's got priority or which one is left, maybe we just say, okay, give everybody some time. You need to decide how much time that is. And we call that the time quantum. Give it to a process, and then when that time is due up, we preempt that process. We say you've had enough CPU time to go, give somebody else a shot, on your bike, back into the ready queue, and we'll take the next one in line. So we try to be fair. We give each process a certain amount of our fixed CPU time. That's quite nice if we have a certain number of processes. So say our time quantum is 10 and we have 5 processes. We know that nobody will ever wait more than, well, we have 5 processes and there's 4 of you in the queue and 4 of them take 10. No process will ever wait more than 40. That's what this bit in here means. N minus 1 times Q. So we know that nobody will wait too long, in essence. Now that doesn't always work, and I've mentioned this before, and you've all seen it on your systems. When you have so many things running, it can still take time. That's what's happening here. Everyone's getting time, but there's so many things going on that time gets longer and longer and longer and longer till it feels as if nothing's happening. It is, you just haven't got there yet. We also have to be careful with our Q value. This isn't Q as in waiting for things, this is time quantum value of Q. How big should it be? How much CPU time do we give processes? Clearly we want to give them enough time to do something useful. If the time is big enough, actually, round robin becomes first in, first out, because every process can get its CPU time and finish in the time we've given it. But of course, if Q is large, then processes are waiting longer. They're waiting n minus 1 times Q time units. So number of processes minus 1 times our time quantum. So maybe we should make the quantum smaller so that we get to the other processes more quickly. Problem with that is when we go back to the stuff that we were talking about earlier with our dispatcher. Remember that we have to do stuff. Changing processes isn't without cost. So every time we change a process, it costs us time. So the smaller we make Q, the more time we spend switching processes. And again, I guarantee you've seen that on your system as well. Particularly where those processes have actually been stored on secondary storage, and your system actually spends more time loading things in from your hard disk than it does running anything. So that's why I said right at the start, this is going to be about balance. We want to get Q as right as we possibly can to give the processes a reasonable amount of time to run, but not have to wait too long, and to have it so that we are not spending all the time swapping processes rather than doing some work. So with those things in mind, we can start modeling it. So here's an example of round robin, but here we've had to specify what our Q value is, what our time quantum is. Those of you that have noticed will see that we're back to our very first set of processes, P1, 2, 3, with burst times of 24, 3 and 3. So we can compare with our very first in, first out example. We are going to give the process 4 somethings of CPU time, 4 periods of CPU time, and we'll do them in the order that they come in. So we have P1, P2, P3, and they will get some time. So at time 0, P1's first, it gets 4. And after 4, we look and say, are you done? No. Well, tough. You're going away. We take some note about things. So, for example, after 4, P1 doesn't have 24 left, it's got 20 left. And we switch it out from the running queue back to our ready queue. We've said you've had enough, we're interrupting you, and you're going back into ready. Because we want to give some time to some other processes. Okay, what's the next process? Process 2 is 3, so process 2 starts, it gets 4, and it only needs 3, so it finishes at 7, and it very conveniently exits. So it goes from running to exit and terminates. So process 2 is done. It keeps forgetting I'm using a pen and I don't know why. So process 2 is done. Process 2 finished at 7. Next one up is process 3, and it will take 3. It starts. It's within its time quantum of 4, so it finishes at 10, and it's also done. So we go back and we start with process 1 again. So at time 10, it gets another 4, taking it to 14, at which point the operating system says, oh, it's time for you to finish. Oh, but there's nothing else waiting. Have another 4. Anything else waiting at 18? No, nothing. Have another 4. Have another 4. Have another 4 until it finishes as well. So this has some knock-on effects on those criteria that we defined for ourselves right at the start. We have a higher average turnaround, how long it takes to finish, but it's a better response. So we're doing things really quickly so that we can at least see that something's happening. The trick comes in choosing Q. Now, you've got a thing in here that says Q is usually, but I would point out 2 things. One is I was talking about different operating systems with different hardware, with different job mixes, and that comes into it. So I'm not keen on the word usually, maybe often. And the other thing to point out is, this is from 2013. The theory stays the same. Whether 10 to 100 milliseconds is still okay now is up for debate. Whether the context switching takes 10 microseconds, so that's not a U, that's a micro, another Greek letter just because you haven't got enough to do. So that's 10 microseconds, or 10 millionths of a second. So the theory stays the same, but the numbers might change. And we can start to work out what that means in terms of our round robin. We can start to look at process times, the time that we give them, the quantum, and how many context switches that has. Not surprisingly, depending on the size of the quantum, as it goes down, the number of switches goes up. And remember, we want to minimize switches as well because that takes time. And we can start to graph it. Because it's very easy to say, oh yeah, let's have the smallest time possible, but the cost of switching becomes high. And we can start to see how that changes. We can start to graph it. In other words, we can model what would happen if we had a time quantum of 1, 2, 3, 4, or whatever. With a set of processes, we can start to model how the turnaround time changes with the different time quantums. And we can come up with a rule of thumb for your operating system, for your process mix. Your time quantum should allow 80% of CPU bursts to be completed within your time quantum. That's a reasonable target. Excuse me. That's a reasonable target to aim for a round robin schedule. Any questions about that? Okay, so we've got all these approaches and they all have positives and negatives in terms of how fast you get to things, how fast they turn around, how long people have to wait. Let's make it more complicated. Let's say that rather than just doing one, let's implement more than one of these approaches. So rather than just having one ready queue, let's have lots. Well, we'll start with 2. Let's say that we split it into 2, one of which is foreground and one of which is background. In other words, things that we are interacting with. This Teams call, for example. Let's make that a foreground activity because we want fast turnaround. We want it to be updated. But let's make PowerPoint here less of a priority. Now, it's not quite background enough to put it into batch. By batch, we mean run it when you can. In other words, when you have no interactive processes still on the go, run one of these batch processes in the background that don't need any interaction. So you might set up a process that says, okay, I'm working with Blender, which is a graphics thing. So you're working with Blender in the foreground, and you might then want to render an image. And you might say to Blender, okay, well, I want to render that image. I'm in no rush. Do that as a batch job. In other words, run it when nothing else is happening. That means that you can still do all their interactive stuff. You'll still get good response time. But when nothing else is happening, you can use up that CPU time with the batch processes. So they don't switch between these. These are multi-level queues. You choose which one you want it to go in, an interactive or a batch one. And you use different algorithms. So for round robin, for foreground, the interactive ones, you use round robin. Give them each a chunk of CPU time to get going. For background, you just say, nah, whatever got there first, we'll do that. Now the scheduling becomes trickier. What we're going to do? Well, we've already said we want to concentrate on our interactive stuff because it is interactive, we want it to happen. But there's a possibility that we never stop doing interactive stuff. So it's the same as it's the same reasoning that we had before with the priority stuff. That we could starve a process of attention because it was too low of a priority. Here we could starve of attention because it's in the background and we never stop doing interactive foreground processes. So instead of saying, well, wait until everything's done, we could say, oh, okay, let's start balancing it a wee bit. I did say we'd talk about this a lot. Maybe say, okay, we'll give 80% of the CPU in normal time to foreground, and we'll give 20% to background. That way we know that even if it's in the background, can be done when you have time, it will be done at some point. Is 80-20 the right number? It depends. It depends on your operating system. It depends on your hardware. It depends on your mix of jobs. It depends, it depends, it depends. And you will see different operating systems taking different approaches. That's why your assessment is written the way that it is, because your assessment says, take all these things that we're learning about in theory and tell me how it works in practice with a particular operating system. So what is it doing for these? Does it have one queue? Does it have lots of queues? What is the mix? Which scheduling system does it use? So that's just for this bit. That's all the sorts of stuff that should be in your assessment. So we could have it working like this, where we've got two. We could make it even more complicated, because why not? We could have multiple queues. We could have queues for system processes that we want to do really quickly. Then interactive processes, then. I think the one thing that we can agree on, that the lowest priority should always be student processes. I think that's, if we can come together in anything, it's that students are lowest priority, don't you think? I'm not seeing any thumbs up. Either you're not listening, or you just don't care anymore. Thank you, Alan, for the shake of the head. Somebody's listening. Oh, Aaron's listening too. The point remains, though, we can have multiple queues and we can decide how we put that mix between them. It does mean that we have to set up a way of moving things between queues. And in fact, this is one of the ways that we implement aging. So we talked about aging before, that if a process was there too long and it wasn't getting any attention, we could move it up. Well, we could start using these as the aging process, moving it up to these different queues. Now, again, there'll be differences for operating systems. We might have different numbers of queues. We might have different scheduling algorithms. We might change how often or when we move up or indeed down a queue. So we need to figure that all out and decide how we're going to implement that. But we've got lots and lots of choices on how we do that. This is just an example of how that might be done. So we have our first queue. It's a fast queue. Time quantum of 8. What we're hoping is lots of processes come in get their 8, and then just exit. And we're done with them. We don't need to think about it. If they haven't, we put them into our next queue where they get longer. 16. So we hope, okay, well, if 8 wasn't enough, maybe 24 is. And hopefully lots and lots will exit at that point. If they don't, well, we'll put them into a third queue, which just says, okay, we'll just do it in the order that they came in. We're still working on all our fast processes. We're still giving a wee bit longer to things that might be finished quickly. But anything else, put them into a third queue and do them in the order they came in. Once again, I'm not saying this is the best approach. I'm not saying this is the only approach. I'm not saying those time quantums are the correct ones. I'm not sure. I'm not telling you that those choices of algorithm like round robin or first come, first served are the right ones. I'm saying it is an approach. And different operating systems use different approaches. Let me give you an example. Now, what I'm not going to do, there's lots of information on the following slides. I am not going to go into it in detail. Partly because it's simply the implementation of the stuff that we've been talking about, and partly because it takes time. So what I want you to do is come back to this and look at it in detail and start to think how that's going to work for each of these types. The other thing I'll point out is that operating systems aren't static. The heading for this one says scheduling through to version 2.5, followed by scheduling from 2.6.23 up. Things change. You might decide to change your scheduling system. So earlier ones had the standard Unix scheduling algorithm. And again, you can come back and you can read this. One thing to point out is this nice thing here. Nice is basically the user saying, please run this process, but be nice about it. It doesn't need to happen anytime soon. So it's saying, give it a low priority in the system. Later on, Linux introduced a new scheduler called CFS, or the Completely Fair Scheduler. Is it completely fair? Well, you tell me in your report. But it does implement multiple scheduling classes with different priorities. And it takes account of both of those things. The highest priority task in the highest scheduling class. And it doesn't go for fixed quantums, it goes for proportions. So it's taking a slightly different approach to give the best throughput for this particular operating system with this particular hardware, with this particular mix of jobs. So these things don't stand still. So we have a mix to take into account when it would need to do real-time responses, and they of course have a higher priority against the lower priority normal ones. Windows does something different. It's priority-based preemptive. In other words, there's priorities for processes, and it will chuck them out of the running queue once it's had its time. So it runs until it's blocked, and blocked is another name for having to move into the waiting queue. We've been concentrating on this bit. We've been concentrating on the I/O. There might be other events. We'll not go into them just now, but there might be other events that stop a process running. It might be that you've split a process into multiple threads and you're waiting on data coming back from all of those threads before the process can progress. It's not waiting in I/O, but it's still blocked. It can't do anything else. So threads will run till they're blocked, they've used up all their time, or something else that comes in that has a higher priority. and it has lots and lots of classes for those. And as we've said before, part of this is down to the programmer. So there's lots of different classes that you can say that a thread or a process should belong to. And again, if you're not into programming, don't worry about it. Just believe me that this is an option that you can invoke. As I said, operating systems don't stand still. When it moved to Windows 7, there was something called user mode scheduling. So remember when we looked at threads and we said the program has got all these functions available in the API? That's one of them. It could decide on its own scheduling. And so there's a whole bunch of priorities implemented. Other operating systems do other things. I'm not going to spend too long on Solaris. Most of you have never heard of it. It's not used that much anymore. But it's interesting to note that it has 6 different classes to cope with a mix of jobs. The idea being that you decide what type of work you're doing and which class it belongs in, and you use different algorithms for different approaches, all within the same operating system. So you have interrupts being the highest priority, coming first in scheduling, real time next, all the way down to timeshare threads. So it takes all these things, puts them into a single priority, and whatever has the highest priority gets to go next. And as with Windows, it runs until it blocks, until it uses up its time slice, or it's preempted. And the algorithm it uses for that is round robin. So, having said all that, having looked at all those things, having decided that there are different approaches, having discovered that different operating systems use those different approaches, the question really is, why? Is there a reason they're using these different things? And can we at some point say this is the best? In other words, can we evaluate these algorithms that we are using and decide which is the best? Well, spoiler alert, the answer is no. But we can try. So here's some of the ways we could try. We've been looking at all these algorithms. We've been giving you different processes with different arrival times and different bus times and all that kind of stuff. Well, maybe we can use those and analyze all these different algorithms on the basis of a set of jobs. So here we've got a bunch of processes with a bunch of bus times. Maybe we can determine which one is best. And of course we can. If we define what it is we mean by best, we can apply each algorithm and say, okay, how do we get on? For waiting time, for example, we can see that non-preemptive another error on the slides, not SFJ, SGF. Non-preemptive shortest job first is 13 milliseconds. So on the basis of this mix of jobs with those bus times and using the single criterion of minimum average waiting time, non-preemptive SGF is the best. Of course, that's only for that mix of jobs. There might be others. Maybe what we can do is, rather than giving specific ones, we can use statistics, because I know you were all desperate today to use some statistics. Just like with the previous ones, again, You don't have to understand the statistics. But what we can do is we can look at systems and say, okay, this is a reasonable approximation of the type of stuff that goes through. And from that, we can then calculate using something called Little's formula. Oh, we've got a lambda now. More Greek letters. You're just in so much luck today. We've got a lambda. We can use something called Little's law. And then we can start to use that to give us an average wait time. As before, if your stats aren't great, don't worry about it. Take, not my word for it, but take the word of the people that do this for a living. This works, and we can use it to start to model how we can have different algorithms. We could, of course, simulate what goes on. How are we going to simulate it? Well, we could get a bunch of random processes. We just get a random number generator and go bang, 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 bang. Random's not wonderful, of course, because what are the parameters for randomness? How long should they be? What's the mix of jobs between 0 and 10, between 10 and 20, between 20 and 30 time quantums? So maybe we can gather that evidence beforehand. Maybe we can get statistics from typical systems. Maybe we could actually look at a real system and get an output from it to say, okay, we ran this process for this amount of time and then that. In other words, get a real set of data from a real working system, shove them through our simulation, and get a whole bunch of statistics out from that. And that's good. That will give us a clue about the best way to approach it. But again, that's only that particular set of jobs, that particular mix running in that operating system, running with that hardware. So we might have to fine tune. And of course, taking a new scheduler, chucking it into an operating system and saying, let's see what happens. Well, it might not be the best approach. So maybe we could just tune it as we're going. And not probably the Windows machine that you're sitting looking at this on, but high-end £20 million mainframes not only allow you to implement different schedulers, and in fact there's a thriving market for companies who don't make hardware or operating systems, they make schedulers for these high-end systems. And you can buy a different scheduler to get your very expensive multi-million pound computer working better. You can pop in that scheduler and then fine-tune the parameters to get the best throughput that you can, or the lowest waiting time that you can, or whatever criteria you're using. But of course, the reason they do that is because you've got a mix of jobs and a mix of hardware, and you're never going to be sure which one will be the best. Questions?
A lot to take in.
Oh, yeah. Normally, I would have taken a break with that one, but because we had so many questions to begin with, we didn't actually start the lecture till half an hour in. So I was worried that if we took a break, I might overrun. So as usual, these are recorded. You can go back and look at them. But yes, go back, look at the slides, and look at the book to get the background on it. And do that in conjunction with the formative assessments, the chapter tests. and that will help you understand which bits are important. Well, it's all important, but to understand which bits I will be concentrating on more. Any other questions? Okay, if there is no other questions just now, let me stop the recording.